module we're going to be looking at, the first lecture for this course, is process vessels and processes. We're going to be looking at separators and how oil is being produced and gas is produced from the ground, and it's taken through the Christmas tree, and oil and gas is separated from the separators, and it goes to various process vessels for processing eventually before it's taken out. So and that is shown on my slide here, and production facility, gas pressure vessels and compressors. Production facility separates the well stream into three components, which we call phases. They are oil, gas, and water. And these phases are then processed into marketable and environmentally suitable products that we can sell to the final consumer, which can be a refinery, which can be some other third-party users for products. Now, when gas and oil is produced, water is also produced and gas is also produced in that facility. So there's a need for us to do what we call separation of the oil, gas, and water. So in this lecture, we're going to be looking at a general overview of the oil production and the various process systems that are required. In subsequent lectures, we're going to be looking at separator designs, and we can look at, for specifically gas, the need for us to compress the gas is required so that we can bring it into some manageable fluid process flow system so that we can put it into pipelines. And to do that, we're going to use a compressor, which is shown on the slide. So there are two types of separators. We have the vertical separator and the horizontal separator. The vertical separator is shown on the board and on the slide here, and the horizontal separator is also shown on the slide. And basically, these two are used in the oil and gas industry and for oil and gas platform. We'll be looking at the design in module 2 of the lecture, and that will now entail us to have some details about how these equipments are being used to separate oil and gas. Let's go to the next slide. Typically, a typical horizontal separator on an offshore platform shows the inlet side. Note the drain valves of various points along the bottom and access platform along the top. So that's shown on the board there. And then we have the compressor. That's basically the compressor is after you've separated the gas from the oil and water, it goes into a compressor. After it's been processed, it goes into a compressor where it's compressed to higher pressure for it to be able to flow inside the pipelines. Basically, there are two types of compressor. We have the centrifugal compressors, then we have the engine, then we have the centrifugal compressors, then we have the engine-driven compressors. Now we're going to be looking at the major items on the process equipment. That's the process instrumentation. Now, for gas facilities like gas compressors and separators, we have instrumentation that provides control, and the need for controlling. So figure 1.25 shows a typical pressure controller and a control valve, and in the black box a signal is sent to the actuator that shuts down the control valve. So these are some of the symbolic things we use to describe a pressure controller. Then we have the figure shows the figure 1.26 shows the self-contained pressure controller. We have different types of controllers. We have the level controllers, we have the flow controllers, then we have doing different things. The level controllers control the flow of either gas, liquid, or water in maybe in a storage tank. Then we have the pressure controllers regulate the pressure in that controllers. We have temperature controllers that regulate the temperature. We have flow controllers that regulate the flow of fluids. Now, the pressure controller valve with a pneumatic actuator and pressure controller mounted on the actuator is shown on the board. Look at it. That's a typical pressure controller. And the need for regulating pressure cannot be overemphasized, because we need to control flow, or else there will be explosion, or else there will be breakage and all of that. And from the safety perspective, we need to monitor our pressure and control it. Now, two self-contained pressure regulators in fuel gas piping system is also shown on the board. This is just to give you a whole general view. We have two external level float controllers and an external float switch is also shown on the board. I'm just showing basic diagrams, and some of you may have gone into the industry, you may have done your IT there, you may have seen some of these things. So for some of you who have not seen these things, it's shown on my slide, and we are you can also have I've also sent these materials for you to also be able to look at them. Now let's go to various components are combined into the production process and must be considered in selecting components for a system, and there's no substitute for experience and good engineering judgment. No matter how technically sound you are, no matter how good a designer you are, you must have experience. You must have someone who has experience of processes, of separators, of compressors, and be able to put all of these so that he can use his judgment and experience where technical and design has failed you, where book has failed you, to be able to provide the instrumentation. So one of the process of controlling process, production facility process, must be controlled at the pressure level and flow. All must be controlled. If they are not controlled, you have a safety issue, and that's not what we want. Control valves are used throughout the process to control pressure, level, temperature, and flow. These are the use of control valves, and these are shown on the board. You can see the symbols of a valve, a check valve, a relief valve, a control valve, a shutdown valve, a choke, a level controller, a pressure controller, a temperature controller, then a flow meter and pumps. All of these are shown on the board. You can just on the slide, so you can see them and you can learn them. You'll be specifically required to annotate a separator. For instance, I will ask you in an exam to annotate a separator, and you should be able to use these symbols creatively and know where to put them and use the right nomenclature for them. Okay, an air cooler, a compressor, you can see some of the symbols. A heat exchanger has the symbol there. A pressure vacuum valve has its own symbol. And all of this you can find in the API 370. So let us look at some of these processes, the differences between the various types of control valves and their procedures for their sizing, primarily based on function of this equipment. Shows a very common single port globe body control valve. All control valves have a variable opening or orifice for a given pressure drop across the valve the larger the orifice, the greater the flow through the pipe. So you can control the flow by controlling the orifice. You understand? When you control the orifice, you control the flow. And this is a typical control valve. There's need to do, and some of these things are used for process equipment like separator. So we have chokes and other control devices that have fixed or variable orifice. So the diagram showing the pressure control. We have so the most common type of controlling pressure with a flow. In most instances, they will, if insufficient gas release, the number of gas in the molecule vapor space increases, and thus the pressure in the vessel increases. In some instances, there will not be enough gas separated, and thus the pressure in the vessel increases. So we need to be able to, under some conditions where there has been only a small pressure drop from the upstream vessel, where the crude GOR gas oil ratio is low, it may be necessary to add gas to the vessel to maintain the pressure, control at all times. So that's very important. Level control. Now, for tanks, storage tanks and everything, and even some pressure vessels, there's need to do what we call level control. Now, we want to control the gas-liquid interface or the oil-water interface in process equipment. This is done with a level controller and a liquid dump. The most common form of level controller is a float. Although electronic sensing device can also be used, if the level begins to rise, the controller signals the liquid dump valve to open and allow the liquid to leave the vessel. If the level in the vessel controller begins to fall, the controller signals the liquid dump valve to close and decrease the flow of liquid from the vessel. In this manner, the liquid dump is constantly adjusting its opening to ensure that the rate of liquid flowing into the vessel is matched by the rate out of the vessel. So that's how you achieve level control. Let's go to the next slide. Now we're going to be talking about temperature control. The way in which the process temperature is controlled varies. In a heater, the temperature controller measures the process temperature and signals a fuel valve to either let or more or less fuel to the burner. In a heat exchange, the temperature controller could signal a valve to allow more or less of heating or cooling media to bypass the exchange. Now we have flow control. It is very rare that flow must be controlled in an oil feed process. Normally, the control of pressure, level, and temperature is sufficient. Occasionally, it is necessary to assure that flow is split into the controlled manner between two process equipments, or perhaps to maintain a certain critical flow through the components. This can be a complicated control program and must be handled on an individual bias. Now we're going to look at the wellhead and manifolds. The production system begins at the wellhead and includes at least one choke unless the well is in an artificial lift. Most of the pressure drop between the well flowing tubing pressure, that's the FTP, and the initial separator operating the pressure occurs across the choke. The size of the opening of the choke determines the flow rate. Now, the positive choke takes over and keeps the production rate within limits should the adjustable choke fall. On offshore facilities, another high-risk situation, an automatic shutdown valve should be installed on the wellhead, and it is required by federal law in the United States and in Nigeria also. In all cases, block valves are needed so that the maintenance can be performed on the choke if there's a long flow line. Figure 2 shows the configuration of a typical storage reciprocating compressor. Gas from the free water knockout FWKO enters into the first stage suction scrubber. Any liquids that may have come through the line are separated at the point of the gas flow on the first stage. So the compressors are used to compress the gas, and any liquids that are coming are separated on the first phase. So the compressor is equipped with an automatic suction shut-in valve on each inlet and a discharge shut-in-out valve. Many operators prefer in some cases that regulations regarding compression be automatic blow down valves, and all of these are subsequently installed to ensure that we achieve this. Okay, so we're going to I'm going to show you how we're going to design compressor. This is a typical compressor three-stage process. Okay, so we see the first compressor, we see the second, we see the third, and we see all the instrumentations on the compressor. So method of calculating. So two basic types of compressors used in the production are reciprocating and centrifugal reciprocating compressors, and they compress the gas with a process with a piston moving linearly in the cylinder. Because of the flow is steady, we must control vibrations. Now, we want to size compressors. So there are formulas by which we do that. Normally, you will probably have. Now, that's the formula for sizing compressors. Now, once you know the ratio, you know the suction pressure, you know the discharge pressure, you can calculate the number of stages in a compressor by this formula on the board, where R is the ratio per stage. You can say, okay, I want to do ratio per stage 0.33. I'll probably give you 0.25, but it will not be exceeding 2.5. Then we can say, okay, we want to get the number of compressors. There's a very funny thing some people do in exam. When they calculate the number of compressors based on that equation, and they get like 3.8, what will you do, student? You probably leave it at 3.8. No, you cannot have half compressors. Or you say 3.5, you cannot have 0.5 compressor. So you upgrade it to the next compressor. So if you have 3.3 as the final calculation for N based on this formula, then you have to upgrade it to 4. So you now say, okay, they need 4 stages to complete. You don't put it at 3 because you will not achieve what your compression is, but you have to put it at the next stage. So if I ask you in the exam and you calculate for N and you get 3.5, upgrade it to the next level. Even if you get 3.3, also upgrade it to the next level. Okay? Because I'll test you on that. Now, when we're able to calculate, so we have also a formula that helps us to calculate the discharge temperature. The discharge temperature is a ratio of the, it's shown on the board. It's shown on my slide. There is the T. You have to find ratio based on their heat capacities, and definitely you now have to do the formula and you get the discharge temperature. Also, the compressor BPH also shown on the board. I don't need to say all the formula. Use that formula and insert all the data that have been given to you, and get the. That is it for the class for today. We have concluded Module 1. In the next class, we'll be looking at Module 2. And make sure you read your lecture notes. And I've also included the exam questions on the board. So go and practice it for the next class. Okay? Yes, in continuing my last slide, we're looking at temperature control. And temperature control involves controlling the temperature of the process vessels for the purpose of achieving a reduction in temperature. Now, these temperatures, they enter into special heaters by opening the valves to allow more fluid or more fuel to enter the gas stream, either to heat the temperature system or lowering how much fuel is entering. Or we can have a heat exchanger where the fluid bypass the heat exchanger also with effect to cool. Then we have the flow control. Normally we don't control flow in the pipeline vessels, but there may be need for us to have flow control when we have like a distribution point, like a T point, where we need to regulate how much flow goes into one pipeline and how much flow goes into the other pipeline. So we now use the pressure control to achieve that. Then pressure control requires us to look at the pressure vessels, and based on the amount of gas inside the pressure vessels, we'll decide whether we want to lower the pressure by releasing some of the gas out through a choke valve of some sort. Then the choke valve does not allow it to come inside, or we want to increase the pressure by introducing gas into the system. So basically, now let us talk about the basic system configuration we're having this thing. Now we have the Christmas tree that has all the choke and all the valves, where oil, gas, and water comes in through the Christmas tree and it goes into the separator. And what we do basically is to separate the gas, the oil, and the water, and the gas go into some processing units, whereby it comes in at the first stage and probably enters some compressors if we want to compress the gas so that we can put it into the pipelines and ship it to some other plants like the LNG or the storage, gas storage facilities. So I will be talking to you on compressors now in this lecture. And when we're looking at compressors, we're looking at stage compressors. And the formula for this is the process flow of a typical compressor. You see all the instruments on the compressors, but there's also a need for us to be able to calculate the number of compressing stages that we need. And once we know the suction pressure and we know the discharge pressure, we use this formula to calculate the number of stages once we know the ratio of compression. Now, the ratio of compression can be 1 torr, can be 2 torr, can be 0.33, and once we know the ratio of compression, then we use this formula to calculate N. There's always a very tricky something. If a student calculates and gets 3.8, for instance, as the number of N, you don't leave it as 3.8. You approximate it to the next value, and you have 4 stages. You can't say, if you say 3.8, you fail, because there cannot be 3.8 compressors. There has to be whole compressors. So even if you have 3.3, you also have to upgrade it to the next level to 4 compressors. So what we're looking at is we can also calculate the discharge temperature by using the specific constants, heat constants, maybe Cp over Z to give K. Then we now use the formula to relate the temperature and the pressure. Now there's a relationship between temperature and pressure. You already know that from the gas laws. So we use that to determine what would be knowing the number, the discharge pressure, the suction pressure, knowing the initial temperature, we can get the discharge temperature. We can also calculate the brake horsepower of the compressor. So you want to be able to know how much power you require. That's the formula on the board, and use that to do the compression. So thank you for listening to this class, and I will be talking to you in the next lecture. And the next lecture we'll be looking at some other specific facility and how to design them. So the class, you can get the assignment from the class rep. I have sent all of that to your email. and we can use that to practice for the next class. Thank you. Good day, students, and this is my second lecture on separator design. So this lecture will be talking about separators. Now we have in the oil and gas industry, separation is one of the most important equipment you have for oil and gas industry, because that's the equipment we use to separate oil, gas, and water. And basically there are three types of separators. We have the vertical separators, we have the horizontal separators, then we have the spherical separators. Then when you want to talk about by classification by what they do, we now have the two-phase separator and the three-phase separator. Now, what we're going to be looking at in this lecture, we're going to be looking at types of separators, and everything is on the board, and I've given you your lecture notes for those aspects. So I will refer you back to my lecture notes so that you can have a proper overview of everything about separation and what it does. So go and read the lecture notes. All I'm going to give you is just an executive summary, and we're going to be looking at the principles of separation, the factors influencing oil and gas capacity, and the basic procedure for separation sizing calculation. So what we want to do basically is that we want to be able to understand the basic theory of separation. Now, separation by itself must operate on certain physical properties, and one of the important physical properties we're looking at is gravity and density. Obviously, after gas we have oil, then we have water. So if oil, gas, and water enters into a vertical or horizontal separator, by virtue of their densities, you can achieve what we call separation, because the gas will be on top of the oil will be on top of the water. You can drain the water from the ground, from the outlet nozzle, then the gas can go into the mixer structure out of the system. Then what you have is oil. Then you can have separation. So we have achieved separation of those three things. So basically, the principles of separation must incorporate momentum. Fluids with different density have different momentum. You understand? Because the formula for momentum is density times V, or mass times velocity squared, mass times velocity, sorry, and that is momentum. And mass is associated with density. So the more dense the liquid, the more it has momentum. The faster it goes, the more it has momentum. Now, gravity settling could also be a principle we have to look at to be able to understand why separation. Like I taught you in Stage 303, different if you put a solid material inside fluid, it begins to sink by virtue of its density, and it reaches its terminal velocity. So also, if a fluid, that's a liquid fluid, is flowing in a gas stream, different like oil and water, we have different terminal velocities because they have by virtue of their different densities. So by virtue of their terminal velocities, you can separate the water and the oil particles. So we have the concept of gravity settling. Now, each of them have different weight and they will settle at different terminal velocities. So by virtue of the liquid droplets, they settle at different terminal velocities. Then smaller droplets coalesce and they form bigger droplets. So that is one of the principles we're going to be looking at in terms of separation. Now, factors influencing gas and oil capacity. We have the physical and the chemical properties. Now, on the physical properties, we have the specific gravity, viscosity, and phase equilibrium. Those are physical properties we are going to be looking at. Like oil is more in terms of in terms of density, that's specific gravity. Water is more dense than oil, but oil has more viscosity, and that affects the way the fluid flows. Then in terms of phase equilibrium, how much of the gas is in the liquid and how much of the gas in the vapor phase. Now, we're going to be looking at size and distribution of liquid particles, gas upstream of separator mixer structure. And we're also going to be able to know exactly the operating temperature, the operating pressure, varying gas-liquid ratio, liquid level momentum, the influx of foreign materials, and also we're going to be looking at the well fluid pattern to be able to design separators. Basically, we have the design arrangement. Now, the basic procedure for doing separation is shown on the board. So I'm going to allow the slides to roll so that you see the various procedures. One of these is that we have to calculate the various lengths and DLEFF, and we have to calculate the drag coefficient. Now, let me give an example. Once we know the volumetric flow rates and we know the volume, then we can calculate by virtue of the volume is the area, the volume times the to calculate the volume, we have to know the diameter, we have to also know the length. So that is equal to the volume of the separator. Then if we have the flow rates, we'll know exactly what we call the resident time, which is called the retention time. So once we're able to fix the retention time for, like, say 3 minutes, once 3 minutes the retention time, we know that if you divide the flow rate by the volume, then we'll get the TR. Then once we are able to know the resident time, then we can be able to say, okay, let's have a resident time of 3 minutes, then we can calculate all of this. So all of this have been shown on the slide, and I will advise you to go home and study these materials yourself and do that. So I would like also for you to try your hands on one of the examples I've given on the board. So once you go to your various places, try and solve some of the problems I've given to you on separation. Now, separators are very important in the oil and gas industry, and we have some that are suited for deep offshore, offshore and onshore operations. So with deep offshore, you know that it is better to have a horizontal separator because it's not difficult to have long towers of vertical separators because of height and this. So you put it as a horizontal separator. But in an area where you need space, horizontal separators may not be very good, so you use vertical separators to do that. So basically, once you're able to achieve some level of separation, then we can now transform all the other things to gases. So I have a whole lecture note on separators and separator design. Make sure you read those lecture notes. And we're going to be doing a term paper. And that term paper involves you to design a separator and a compressor. And part of the design is that you are going to annotate a separator, annotate a compressor, and a flow system. Now, I've also presented this on the slide. Is here the procedure you use to design your term paper. First of all, you have to know your introduction, do your introduction of the term paper. Then you now look at the problem statement to determine how you want to do your process flow diagrams and also your P&ID diagrams for both the separation units and all of that. So I'll expect you to finish this term paper within 2 weeks. By August 30th, you should have submitted your term paper and all your assignments for the purpose of the exam. So if you have any questions, I'll take them later. Come to my office. I'll be able to help you with that. Thank you. Students, I am here to give you the last lecture, which has to do with hazard and safety and how you design safety charts. Now, the most important document you get is API ROC. I want you to go and read those materials. It's posted on your emails, and I have also been able to do that in this presentation. You see that on the slide. Then the slide for the safety is all encompassed here and all of that. So in safety, we have to look at different aspects of safety, methodologies of safety. We have using the failure mode analysis to analyze safety. We have using the fault tree. We have hazard. These are the safety analysis you will do on the process. So once you get a process, there's need to have safety, and there are different types of valves that we use to be safe. Like the check valves only allow flow to go in one direction. Then we have emergency shutdown valves, and we have the alarm circuits units. Then we have even when you annotate a separator, you have to put all the various pressure controls we aim to achieve safety, monitor pressure, temperature, and flow, so that you can impose a safety control system. Now, what we want to do is that in the oil and gas industry, safety is a very important component we look at. Without safety, it's better to design for safety than design for profit. It's better to design for safety than design for the equipment itself. So the oil and gas industry needs you to be able to, in equipment design, you need to be able to say, okay, fine, what are the hazards, all the hazards in this process, and what are the hazards? That means hazard analysis. It comes through using a very solid technique called hazard, where you now do all the hazards, where you list out all the hazards, all the implications, all the primary and secondary implications of those hazards. So one way to classify them is using failure mode effect analysis. One of the ways is that you look at the failure modes and you look at all the effects it can create. For example, if you have a pump that is shut down intermittently, how does it affect the safety of the separator or the safety of the storage tank? If you have a check valve that is faulty, whether the backflow will destroy the separator. So all of these hazards, if you have a leak, cause explosion, fire, and all the other things. So one of the ways to classify this is to put it under a table called the failure mode analysis. Another way to look at it is using the fault tree. And using the fault tree, you'll be able to design a primary event that leads to a top event. That means how does the primary event add up to each other to lead to a bigger event. Another way to look at safety is to use the bow tie, where you analyze the hazards, the threats of those hazards, then what are the safety controls in place that you have put, and the final release of containment. So if you're able to put all of that in the bow tie, you'll be able to see all the safety architecture. Another way to look at this is to look at a safety chart. And one of these charts is to be able to bring you to whether it's a high mode or high-low mode, or whether for pressure, temperature, and all of that. So I will allow the slides to roll so that you can see other forms of safety. I've been able to design a leak detection system as well that is used in the oil and gas industry to really check, manage the risks of pipeline failure related to leaks. And one of the ways I was able to do that was able to look at certain criteria, response time, alarm thresholds, and all these robustness and all of that, and come up with a leak detection system. So we will be discussing more in subsequent lectures. So one of the important documents you should have is API ROC. With the API, you'll be able to know all the safety issues around it. For example, the pressure vessel, compressor, other things that can affect your picture. So thank you for your time. And make sure if you have any questions, please do come and check on me. Thank you.